So let's go over rule number one. There are total 9 rules that I've kind of broken it down into. So first of all, rule one, the oxidation number of an atom of a free element is always counted as 0. What does it mean by a free element? Basically, it means any element that is written by itself that is free of charge, which means it has no superscript. So as an example, these are good examples right here in the bottom. So the example of these sodium, oxygen, chlorine, and hydrogen, because you see no superscript number, that means their total charge is going to equal 0. So all of these oxidation number are considered to be 0. So whenever you see any element that are written by themselves that are not combined together or have multiple of the same thing by themselves, they will always be 0. It's all about that superscript in a sense. It tells you the charge and overall sum, all right? So rule number 2 is basically, well, if those superscripts aren't 0 and they end up having a number. So if it's a monatomic ion that has a positive or a negative charge, that negative or positive charge is going to be equal to your oxidation number. So these are typical examples. So if you encounter any elements that have a superscript number by themselves, again, these end up becoming their oxidation number. All right. So if I were to write aluminium and it has a +3 on the side and I am going into some sort of reaction here, I can easily go along and say that, okay, this aluminium has an oxidation number of +3. So any monatomic ion that is written by themselves, their charge becomes the same as their oxidation number, right? Now, rule number 3, 4, and 5, in a sense, is actually tied together. It has to do with the electronegativity trend. Now, the problem arises, what happens if you have multiple elements combined together? Well, this rule tells you basically the big gist about it. Basically, the oxidation number of the more electronegative atom in a molecule, or that complex ion, ends up keeping their charge according to the periodic table. So you have to first remember how the electronegative trend works on the periodic table. So basic diagram of the periodic table. All right, we have our hydrogen up top here. But remember, the trend of electronegativity on the periodic table increases this way and it ends at fluorine almost at the top of the corner because fluorine has the most electronegative value. Now, according to this rule, because this dictates with rules 3, 4, and 5, as long as you have a higher electronegativity number, that is what will keep its original charge. So what does it mean? So if we were to compare nitrogen and hydrogen out of these two, hydrogen exists over here and nitrogen exists right about here. All right. Now, nitrogen is closer to fluorine, so nitrogen will keep its charge, and their charge up top typically goes -1, -2, and -3, which is where nitrogen stands under, so nitrogen ends up keeping that -3 charge. But if we look on the bottom example here, we have nitrogen and oxygen. Oxygen is actually closer to fluorine, which means early on the example, we identified nitrogen because that had the higher electronegativity. But in this case, because oxygen is more electronegative, it actually ends up it lets us assign the oxidation number for oxygen. And then the nitrogen actually does not end up being 3, but it ends up being +2 in this very particular example. All right. This will be explained around rule 8. Okay. Now, however, as long as you understand this rule, because whatever is more electronegative will keep its charge. Again, rule 4 kind of follows in the same thing. It talks about fluorine. Fluorine is the most electronegative value, which means there is no other element on the periodic table that can beat it in terms of electronegativity, which means fluorine will always keep an oxidation number of -1. All right? Like I said, this ties in with rule 3. And then rule 5 also ties in along with this because rule 5 talks about oxygen. Oxygen is the next most electronegative element compared after fluorine. So oxygen actually keeps its charge of -2 as an oxidation number. However, like all things, there can be exceptions. There is one lone exception for oxygen not having a -2 charge, and that is when it's combined in a peroxide. In a peroxide, oxygens end up actually being a -1. This is the only rare case that you'll ever see oxygen being a -1. All right? Or other than that, if you combine with a fluorine, because fluorine is more negative, electronegative, fluorine keeps its charge and then oxygen becomes positive. But that's the only other case other than peroxides. So if we look at the bottom one, typically these are easy because you only know that there's one exception besides with fluorine that oxygen will be a -1. Other than that, remember oxygens are always going to be -2. All right, so let's move on into Rule 6. According to Rule 6, hydrogens will typically always keep its charge of a +1. Now this is going to sound pretty interesting because hydrogens already have a +1 charge, so it makes sense that it will be a +1 in terms of oxidation number. However, when it combines with any metal by itself, it ends up being a -1 because the metals actually have more of an affinity to become a positive charge than hydrogen does, because in reality, all metals have positive charges. All right, so that's the only case where it will not become. So if you look at, so in case of metal hydride, so if you look on the bottom here, chlorine is a non-metal, which means hydrogen will keep its oxidation number of +1. Whereas over right here, this is a metal hydride, which means sodium will keep its charge and hydrogen ends up becoming a -1. That's how these are assigned. So in terms of these rules, up until Rule 6, it sounds pretty straightforward. Well, Rule 7 is also straightforward as well, because if you remember from our unit from last semester when we talked about valence electron and valence charge, it kind of follows that same rule because we have specific sets of element groups on the periodic table that keep its charge. And in terms of that, we talk about group 1, alkali metals, and group 2 metals, which are the alkaline earth metals. These will always keep its valence electron numbers as their oxidation number. So group 1, so we're talking about lithium, potassium, sodium, rubidium, cesium, and those kind of francium, those elements will always keep its oxidation number of +1. And then group 2 metals like magnesium, calcium, strontium, barium, beryllium, etc., those will always keep a +2 charge. And we have one additional one. Aluminium will always keep its oxidation number of +3. All right, so this kind of makes it easier for us to keep track of certain things in terms of assigning oxidation numbers. All right, so let's look at Rule 8. Basically, Rule 8 combines all the rest of the rules and talks about the ultimate rule of if you don't have any number up top, so no superscripts, that means the total sum of whatever is involved has to add up to 0 because it's a neutral compound. So if you look over here, an example right here, if you look at CaBr2, notice there is no number. That means that the total sum must equal 0. And according to our previous Rule 7, calcium is a group 2 metal, which means it will keep its +2 charge as its oxidation number. Now, since the overall charge is 0, and we have 2 bromines, right? We have 2 bromine. Whatever the charge of bromine is, or the oxidation number, when we multiply it by the quantity and add it with the oxidation number of calcium, it has to add up the total charge sum, which means the only available oxidation number for our bromine is a -1, giving us our oxidation number options such as. All right, so if you look at these, this is just about basic numbers. Aluminium has a quantity of 2, oxygen has a quantity of 3, and according to the rules, oxygens will always be a -2, and aluminiums are always going to be a +3. Let's check out the math if it makes sense, because there is no number up top, which means the overall total sum is 0. And if we do the math here, it becomes +6 minus 6, which is 0. So that makes sense. Now, these are what we're talking about. Now we're kind of gathering and finalizing all of these rules together. Then we talk about rule 9, our last one. What if the sum doesn't end up being 0? Well, if there's a positive or a negative number, that actually becomes a total sum of your oxidation numbers. So, not to be worried about. So if we have that -2 up top here, that means our total sum is going to end up being -1. Now, out of these two, S and O, remember the rule of electronegativity. O is more electronegative, which means we assign O with its original charge of -2. But we have 3 oxygens, so we multiply that. So the total oxygen is -6. Now, we don't know what the charge of sulfur is, but whatever it is, when we add the 2 together, it has to end up becoming a sum of -2. Which means the only option for sulfur in this example is going to be a +4. And that's how we can guess, well, calculate oxidation numbers. All right. So let's talk about our last finalizing here. We have oxidizing and reducing agents. When we talk about oxidizing and reducing agents, remember that relationships, when I talked about when something is being reduced, it can't exist without some other thing being oxidized because of the electron transfer, right? So basically, what the oxidizing and reducing agents mean are, well, if something is being oxidized, it's coming from the electrons that are gained from the reduced, which means whatever is being reduced helps whatever is being oxidized become oxidized. That sounded really complicated. In a sense, if we have A and B, and A is being oxidized and B is being reduced. Now, if A is being oxidized, that means B helps A become oxidized. So that B that helps A become oxidized becomes our oxidizing agent. It's whatever helps the oxidized become itself as the agent, whereas we know that A contributes into B becoming reduced, which means A is also our reducing agent. So the agents, in a sense, are basically the opposites of what they actually end up doing, because remember that relationship of one cannot exist without the other. That means if one is being oxidized, it's also going to help the other become reduced. So that's how we finalize these terms of oxidizing and reducing agent. So let's look at this brief example right here. So if we look at these, I'm going to put the oxidation number up top and the overall oxidation numbers on the bottom so we can keep track. Now, magnesium over here is standalone. It has no charge, which means the oxidation number can only be 0 in this case. So the overall oxidation number is 0, and that satisfies that overall, right? The next one, we have HCl. H always going to be a +1. So our total sum over here tells us it's going to be 0. So whatever that chlorine is going to add up. When we sum it up, it has to equal 0, which means chlorine can only be a -1. Now, out of these two, we have Mg and Cl2, but Mg is a group 2 metal, which means it will always have a +2. Now, in our case here, we understand that there's going to be 2 chlorines, right? But the sum is going to be 0. So whatever the sum here has to equal 0, but there's a quantity of 2, however many of that charge, which means only a -1 should satisfy that when you add it up, and it becomes 0. All right. Next one, we also have a total sum of 0, but we understand that it's a monatomic ion that's free. Well, it's not a ion, but it's free standalone, so it has an oxidation number of 0. Now we get to write half reaction, and half reactions are basically writing the half, oxidation half, and the reduction half of the reaction. So remember, loss of electrons are for oxidation, so we're looking for numbers that go up. And if we look at magnesium, we'll notice that magnesium starts at 0, and it goes to +2, so that lost electrons. So we can write the oxidation half as Mg going into MgCl2. And when we are looking for a reduction, is gain of electron, which means the oxidation number goes down, which we can see in HCl going to H over here. All right, so this should explain these right there. which then helps us finalize the rest of oxidizing agent and the reducing agent.